Right now, hundreds of colossal galaxy clusters are hurtling through space at over 2 million miles per hour towards something completely invisible. You might believe the observable universe reveals everything there is to see, but you'd be wrong. We're living inside a massive cosmic bubble, 93 billion light-years across. Yet this enormous sphere is nothing more than a tiny fleck compared to what lies beyond. Out there, new universes spark into existence like bubbles in a vast cosmic sea. Invisible threads known as cosmic strings slice through the fabric of reality, and white holes, opposites of black holes, spew entire galaxies from pure energy. If you're ready to journey beyond the boundaries of human vision, brace yourself. We begin. The number that will bend your mind is 93 billion. That's the estimated width of our observable universe from one edge to the other. 93 billion light-years filled with stars, galaxies, and interstellar dust. It feels complete, doesn't it? Like that's all there is. But it isn't. Here's where things get strange. The universe began just 13.8 billion years ago with the Big Bang. And since light moves at the ultimate cosmic speed limit, how is it possible that we can see objects sitting 93 billion light-years away when light has only had 13.8 billion years to travel? It sounds impossible, but the explanation unlocks our first glimpse of what lies beyond what we can see. Space itself has been stretching since the dawn of time. Imagine drawing dots on a balloon, then inflating it. The dots drift farther apart, even though they never move across the surface themselves. That's exactly how our universe behaves. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us. But during the eons that light spent racing through space, the universe kept expanding, carrying that same galaxy far, far away. Today, that galaxy's light finally reaches us. Yet the galaxy itself now sits some 93 billion light-years from Earth. The light we see shows its ancient past, frozen in time, while the space between us has stretched dramatically. This expansion formed the bubble we call the observable universe. Within it lie roughly 2 trillion galaxies, every star that twinkles in the night sky, every spiral caught by the Hubble telescope, every quasar and nebula. All of them exist inside this vast sphere of visibility. Scientists call it observable for a reason. It's simply the part we can see. Beyond that lies a barrier we cannot cross. But this barrier isn't made of matter, energy, or dust. It's built from time itself. Light from beyond the 93 billion light-year edge hasn't had enough time to reach us yet. Some of that light is still racing across expanding space right now, carrying glimpses of galaxies that no one on Earth has ever seen. Millions of years from now, humanity may finally catch those first photons and witness new corners of the cosmos. Here's the reality that shatters perspective. Our entire 93 billion light-year bubble is just a microscopic patch of what truly exists. The real universe stretches endlessly beyond what our instruments can detect. Picture standing on a beach, staring at the horizon. You might see only a few miles of ocean, but you know vast continents and unseen islands lie far beyond your view. That's exactly how cosmic space works. Past our cosmic horizon, billions of galaxies still swirl around supermassive black holes. Stellar nurseries forge new suns, planets orbit distant stars, and perhaps other regions of the universe obey entirely different physical laws than our own. What makes this even more mind-blowing is that the universe never stops expanding. Every single second, the most distant regions of space rush away from us faster than light itself can travel. We'll never be able to see them. They exist in a realm permanently beyond our reach. The 93 billion light-year limit isn't a wall. It's a window showing us only the nearest chamber of an infinite cosmic mansion. And what hides behind the rest of that mansion? The answer goes back nearly 14 billion years. About 380,000 years after the Big Bang, the universe caught fire. But not the kind of fire you've ever seen. The entire cosmos blazed with light so intense that nothing could escape it. Photons ricocheted wildly, bouncing between particles like trapped sparks in an endless storm. Space itself glowed white-hot, reaching temperatures of over 10,000 degrees. Back then, the universe resembled the inside of a star, chaotic, bright, and unbelievably dense. Free electrons darted in every direction, constantly colliding with photons and scattering them. Light couldn't travel more than a few feet before hitting something. If you were somehow there to witness it, you wouldn't see beyond your immediate surroundings. The entire universe was completely opaque. Then everything changed in an instant. As the universe expanded, it cooled. electrons finally slowed down enough to attach themselves to atomic nuclei. For the first time, stable atoms were born. With no more free electrons to block their path, photons were released. Light broke free and streamed across space in straight, unbroken lines. This was the universe's great moment of liberation, a burst of radiance that illuminated everything in existence. Scientists call this event the surface of last scattering. The light from that moment still travels through the universe today as the cosmic microwave, background radiation, the oldest light we can ever observe, and that ancient flash of brilliance forms the ultimate barrier to our vision. Beyond it lies the true universe, vast, unknown, and forever hidden from our sight. The cosmic microwave background marks the first light that ever escaped from the newborn universe. We can detect this faint glow coming from every direction in the sky. It surrounds us like a luminous shell stretching 93 billion light-years away. This glowing boundary defines the absolute limit of what any telescope will ever be able to see. Imagine trying to peer through an endless fog. Beyond it, everything vanishes. The cosmic microwave background acts exactly like that fog, except it isn't made of mist or vapor. It's made of ancient light, released when the first atoms formed. Anything that occurred before 380,000 years after the Big Bang remains hidden forever behind this radiant wall. We cannot look back to a time when the universe was opaque. We cannot witness the birth of the Big Bang itself. We cannot glimpse the cosmic events that shaped the universe's first moments of existence. But what puzzles scientists most about this ancient barrier is its uniformity. The cosmic microwave background appears almost perfectly even in every direction. Across the entire sky, its temperature changes by only the tiniest fractions of a degree. That shouldn't be possible. How could regions of space that were never close enough to share energy somehow end up at exactly the same temperature? Picture filling a bathtub using two faucets at opposite ends, each pouring in water of completely different temperatures. Yet when the tub is full, the entire bath ends up perfectly even in warmth. That's essentially what happened to the early universe. This smooth uniformity proves that something extraordinary occurred before the wall of light appeared, something that hints at the vast and infinite cosmos beyond our perception. Now consider the numbers. If you count every star visible to the human eye, you'll reach about 9,000. Peer through the most powerful telescopes, and that number explodes to 2 trillion galaxies, each one holding hundreds of billions of stars. The total number of stars in our observable universe is so immense that counting them would take longer than the universe itself has existed. And yet, all of that, every galaxy, every star, every atom represents almost nothing compared to what lies beyond our sight. Our observable universe stretches 93 billion light-years in every direction, forming a massive sphere that contains everything humanity can possibly detect. Every image from a telescope, every glowing nebula, every faraway quasar, all of it exists within this cosmic bubble. Now here's where geometry reveals something astonishing. If you could travel 93 billion light-years in any direction, you'd reach the edge of our observable horizon. From that new vantage point, you could look outward and see an entirely different sphere of visibility, also 93 billion light-years wide. Some galaxies would overlap with what we can see from Earth, but enormous regions would be completely new. An alien civilization living at the farthest edge of our visible universe would gaze upon roughly 2 trillion galaxies that we'll never see. Travel another 93 billion light-years beyond them, and you'd find yet another set of trillions of galaxies, unique and untouched. Keep going in any direction, and the pattern repeats forever. Scientists studying the cosmic microwave background have discovered that, on the grandest scale, space appears perfectly flat, and a flat universe carries a profound implication. It means the cosmos is either truly infinite or so vast that it might as well be. If it is infinite, then infinite galaxies exist beyond our cosmic horizon. Infinite stars, infinite worlds. This isn't wishful thinking. It's what the mathematics of cosmic expansion and the geometry of space strongly suggest. Somewhere beyond our horizon, galaxies identical to the Milky Way spiral around monstrous black holes. Planets just like Earth orbit suns almost identical to our own. The same physical laws that created our world have likely played out countless times in places we will never reach. Here's the most astonishing part. Because space itself expands, Galaxies sitting at the very edge of our observable bubble are moving away from us at nearly the speed of light. Anything just beyond that edge recedes even faster, so fast that light from those galaxies will never reach us. No matter how advanced our telescopes become, we will never see them. Cosmic expansion acts like a one-way mirror. We can observe the ancient light coming toward us, but nothing we send can ever reach back. Those galaxies exist in a realm completely disconnected from our own, beyond communication, beyond contact. Every second that passes, thousands of galaxies drift past this cosmic event horizon, disappearing forever as space carries them beyond the point of no return. And yet, something beyond that invisible frontier appears to be pulling on us. Galaxy clusters that should be spreading apart evenly are instead moving in the same direction, drawn toward an unseen force. According to our understanding of cosmic expansion, every galaxy cluster should drift away uniformly, like dots painted on an inflating balloon, each one receding from the others based only on its distance. That's what astronomers expected to see when they began measuring galactic motion back in 2008. But the data told a different story. Hundreds of massive galaxy clusters were found streaming through space at over 2 million miles per hour, all racing toward the same region of the sky. This vast migration stretches across billions of light years and shows no sign of stopping. The clusters appear to be moving independently of the universe's overall expansion, as though being dragged by some invisible force beyond the boundaries of what we can see. NASA astrophysicist Alexander Kashlinsky and his team gave this mysterious motion a name: dark flow. Like dark matter and dark energy, its true nature remains unknown. But one thing is certain: something beyond our observable universe is powerful enough to pull entire clusters of galaxies toward it. And whatever it is, it lies hidden in the darkness, beyond the limits of human sight. Unlike the normal expansion of the universe, which pushes everything apart evenly in every direction, dark flow drags entire clusters of galaxies toward one particular patch of the sky, located between the constellations Centaurus and Vela. And here's what makes this phenomenon truly unsettling. When researchers calculated the amount of gravitational force required to pull galaxies at such incredible speeds, they found that nothing within our observable universe comes close to having that kind of power. Not all the stars, galaxies, dark matter, or even the largest black holes combined could produce the pull strong enough to explain dark flow. The source of this mysterious tug must lie beyond the limits of the space we can see. Think of leaves drifting downstream on a river. You can watch the leaves moving, but the waterfall that drives the current is hidden around a bend. Dark flow is the cosmic version of those. Floating leaves, galaxy clusters being carried along by invisible forces from something beyond our cosmic horizon. So what could possibly be massive enough to pull entire clusters across billions of light years? The leading theory points back to the earliest moments of creation, cosmic inflation, the brief period right after the Big Bang when space itself expanded faster than light. During this inflationary burst, vast concentrations of matter could have been pushed beyond the visible edge of our universe. These colossal structures, unlike anything we can observe today, might contain the combined mass of millions of galaxy clusters, packed into regions larger than our entire observable cosmos. Or perhaps they're made of exotic matter, obeying physical laws we've never encountered. Other scientists suggest even wilder possibilities. Maybe dark flow is the result of gravitational leakage from neighboring universes. Or perhaps it's caused by cosmic strings, one-dimensional cracks in the fabric of space-time stretching across the multiverse. Some recent studies have challenged whether dark flow truly exists, arguing the observed motion could be the result of measurement error. But other teams continue to find evidence supporting the reality of this mysterious cosmic current. The debate remains fierce, but one truth stands firm. If dark flow is real, then something unimaginably massive lurks beyond the edge of our universe. And perhaps that same hidden realm has already scarred our cosmos. Deep within the constellation Eridanus, space itself appears wounded. Astronomers have discovered a vast cold spot in the cosmic microwave background, a region of space stretching nearly 1.8 billion light-years across that. Contains around 100 times less matter than expected. It's as though something reached through reality and scooped out a massive section of the early universe. Scientists call this strange region the CMB cold spot, and by every known rule of physics, it shouldn't exist. The cosmic microwave background is the fading afterglow of the Big Bang, the first light that escaped once the universe became transparent, 380,000 years after its birth. This ancient light should be smooth, showing only the tiniest temperature variations across the sky. But the cold spot violates that pattern, displaying a temperature drop so extreme that pure randomness can't explain it. Imagine a calm pond after you drop a stone in. Ripples spread out evenly in perfect circles. Now imagine walking up to that pond and finding an area where the water has vanished entirely, leaving a dry patch surrounded by normal ripples. That's what the cold spot looks like in the cosmic data, an impossible emptiness, etched into the oldest light in existence. The most mind-bending explanation suggests that this cold region is the result of a collision between universes. According to the theory of eternal inflation, our universe is just one bubble in an ever-expanding multiverse. As inflation slowed inside our bubble, others continue to form nearby. Sometimes two of these cosmic bubbles collide before their boundaries harden into separate realities. Such a collision would leave behind a circular scar, a permanent distortion in the cosmic microwave. Background computer models predict that these impacts would create perfect ring-like patterns in the CMB. In 2010, scientists believed they had found 4 such circular shapes matching the predicted signatures of universe collisions. But deeper statistical analysis suggested they might simply be random noise. Later, the European Space Agency's Planck satellite took even more precise measurements and failed to confirm the collision theory. Other explanations for the cold spot include the presence of a cosmic void, a vast, empty region containing very few galaxies. These voids can cause temperature dips through a process called the integrated Sachs-Wolf effect, where photons lose energy while climbing out of gravitational wells created by matter concentrations. Some physicists go further, proposing that the cold spot may hint at extra dimensions, or even a breakdown of Einstein's general relativity on a cosmic scale. Others think it could expose flaws in how we understand dark matter and dark energy themselves. Whatever the cause, the CMB cold spot remains one of the most confounding anomalies ever observed. Whether it was carved by a neighboring universe, exotic matter, or an unknown physical process, one thing is clear: our picture of the early universe is far from complete. And the mystery deepens even further when we realize this. Space itself can move faster than light. Einstein's special relativity sets an unbreakable speed limit for anything with mass. Nothing can reach or exceed the speed of light. That law governs every atom, every wave, every force in existence. But the expansion of space itself plays by different rules. During the first moments after the Big Bang, the universe went through a burst of cosmic inflation, a period of unimaginable growth. In less than 1 second, regions of space expanded by factors of 10^26 or more. A patch of space smaller than a proton ballooned to the size of a basketball, or even larger, in the blink of an eye. And it's in those faster-than-light moments that the seeds of every galaxy, every star, and every world, including ours, were born. Unlike cosmic expansion, which evenly stretches space in all directions, dark flow appears to drag entire clusters of galaxies toward a single region of the sky, between the constellations Centaurus and Vela. What makes this phenomenon truly unsettling is the sheer gravitational force it implies. When researchers calculated how much mass would be needed to move galaxies at such incredible speeds, they found that nothing within our observable universe comes close. Even when combining every galaxy, cluster, dark matter halo, and supermassive black hole we know of, the total still isn't enough to account for dark flow's mysterious pull. The only logical explanation is that something beyond the observable universe exerts this immense gravitational influence. Imagine leaves floating on a river. You can watch them drift, but the waterfall driving the current lies hidden around a bend. Dark flow is the cosmic equivalent of that unseen current. Galaxy clusters are being tugged by something invisible, existing beyond the limits of what we can see. The leading theory suggests that these gravitational forces could originate from structures formed during cosmic inflation, the lightning-fast expansion that followed the Big Bang. During that brief moment, space itself grew faster than light, pushing vast concentrations of matter far beyond our cosmic horizon. These regions might contain the mass of millions of galaxy clusters compressed into areas larger than our entire visible cosmos. Or they could be composed of exotic matter governed by physics unlike anything we understand. Other scientists propose even more mind-bending possibilities. Dark flow might result from gravity leaking through from parallel universes, or be evidence of cosmic strings, one-dimensional cracks in space-time stretching across the multiverse. Though later studies questioned whether dark flow exists at all, calling it a measurement error, new analyses continue to find traces of this cosmic current. If real, it implies something unimaginably massive lurks beyond the edge of reality, perhaps where our universe once collided with others. Deep within the constellation Eridanus, astronomers have found another cosmic oddity, a bruise on the universe itself. This vast region, spanning 1.8 billion light-years, shows up as a cold spot in the cosmic microwave background, the faint afterglow of the Big Bang. Within this region lies far less matter than expected, as if something had reached across time and scooped a chunk out of the early universe. This so-called CMB cold spot should not exist. The cosmic microwave background, CMB, should show only tiny temperature variations, yet the cold spot is drastically cooler than surrounding regions, far too extreme to be random chance. Imagine a still pond where ripples form perfectly, but one area is mysteriously dry. That's how the cold spot looks when mapped by astronomers. One of the most fascinating explanations ties back to the multiverse. According to eternal inflation theory, our universe began as one bubble within a vast, ever-expanding multiverse. If two of these bubbles collided before their boundaries solidified, the impact could leave behind visible scars in the CMB, exactly like the cold spot we see today. Simulations show that such cosmic collisions would produce circular patterns in the background radiation. Some studies have even identified 4 of these circles, though statistical analysis later questioned their authenticity. Alternative theories suggest the cold spot may have formed from a gigantic cosmic void, an underdense region of space where few galaxies exist. These voids can create cold regions in the CMB through the integrated Sachs-Wolf effect, where photons lose energy climbing out of gravitational wells. Still, others speculate the cold spot could be evidence of extra dimensions, deviations from Einstein's general relativity, or even flaws in our understanding of dark matter and dark energy. No matter the cause, the cold spot remains one of the most haunting mysteries of modern cosmology. It's a reminder that the universe may still bear scars from collisions with realities beyond our own. The strangeness deepens when we consider that space itself can move faster than light. Einstein's special relativity limits how fast objects or energy can travel through space, but space itself can expand at any rate. During cosmic inflation, the universe grew exponentially. In less than a second, a region smaller than a proton ballooned to the size of a basketball. This expansion happened far faster than light could travel that distance. Picture 2 ants on opposite sides of a deflated balloon. When the balloon inflates rapidly, they drift apart. Not because they're walking, but because the surface carrying them expands. Galaxies behave the same way. They don't travel through space faster than light. Space itself stretches and carries them along. This distinction lets the universe expand faster than light without breaking physical laws. During inflation, regions once close enough to exchange heat and light suddenly became separated by distances light could never cross. That's why the cosmic microwave background appears nearly uniform. Before inflation, everything was tightly connected like a grain of sand. Afterward, those regions became forever isolated. Even now, cosmic expansion continues, accelerated by dark energy. Galaxies beyond a certain distance are receding from us faster than light. We can still see their ancient light, emitted billions of years ago when they were closer. But any light they emit today will never reach us. This creates a cosmic event horizon, a boundary beyond which no information can ever arrive, similar to the edge of a black hole. This horizon currently lies about 16 billion light-years away and keeps growing. Expansion doesn't just change what we can see, it defines which parts of reality can interact at all. Beyond certain cosmic distances, regions of space are forever cut off from one another. The process that birthed our universe continues elsewhere, generating countless new universes in an ever-growing multiverse. In the earliest moments after the Big Bang, a mysterious inflaton field drove this rapid expansion. As it decayed, it released immense energy, forming matter, radiation, and the first stars. Yet inflation didn't end everywhere at once. In most regions, it still continues, endlessly creating new bubbles of space-time, each with its own laws of physics and fate. Think of boiling water. Each bubble of steam forms randomly, independent of the others. Similarly, our universe is just one bubble in a cosmic sea, surrounded by countless others forming every instant. Quantum fluctuations decide where and when these bubbles appear, in an unpredictable but eternal process. Even though new universes form constantly, most of space remains trapped in this eternal inflation, stretching forever. This mechanism produces an infinite multiverse filled with bubble universes, each with its own Big Bang, galaxies, and perhaps life. Some bubbles may contain familiar physics, others could follow entirely alien laws. Occasionally, two of these bubbles form close enough to touch before the space between them expands too far. When that happens, universes collide, sending shockwaves through both realities. At the smallest imaginable scale, even empty space boils with activity. Below the Planck length, about 1035 meters, the smooth fabric of space-time dissolves into a restless sea of quantum foam, where reality itself flickers in and out of existence billions of times each second. At the smallest imaginable scales, reality itself flickers like static. Virtual particles constantly appear and vanish within moments so brief that no clock could ever record them. This restless activity, known as quantum foam, doesn't just ripple through empty space. It may be the very mechanism that forges new universes. Right after the Big Bang, during the inflationary era, tiny quantum fluctuations in the mysterious inflaton field dictated where inflation would stop and where new cosmic bubbles, new universes, would begin. These fluctuations occur randomly everywhere throughout the endlessly expanding multiverse. Here's how it happens. The inflaton field carries an energy value responsible for the exponential growth of space. Random quantum disturbances sometimes nudge this energy slightly higher or lower in small regions. When the field's energy dips below a critical threshold, inflation halts locally, transforming that patch of space into ordinary matter and radiation, effectively birthing a new universe. These quantum events unfold by pure chance, governed by probability. In any given region of inflating space, there's a measurable likelihood that a fluctuation will spark the formation of a bubble universe within a fraction of a second. Multiply that probability by the infinite volume of space still inflating, and you end up with an infinite number of new universes constantly coming into existence. The numbers are beyond comprehension. Every second, countless quantum fluctuations generate brand new bubble universes scattered across the infinite multiverse. Each bubble experiences its own Big Bang, evolves its own physical laws, and forms its own galaxies and stars. Most of them remain eternally separated, isolated by the never-ending expansion that surrounds them. You can imagine the process like seeds blowing in the wind. Most fall on barren ground, never sprouting, but some land in fertile soil and grow into vast ecosystems. In the same way, these quantum seeds occasionally bloom into entire universes, cosmic ecosystems born within the infinite ocean of inflation. The implications are profound. If quantum fluctuations can generate an infinite number of bubble universes, then every possible version of physics must exist somewhere in the multiverse. There could be bubbles where gravity repels instead of attracts, where electromagnetic forces reverse polarity, or where time flows backward, sideways, or even in multiple directions at once. Some of these universes might have physical constants perfectly balanced for life, while others remain lifeless wastelands, places where stars never ignite or matter never binds together. A few may operate under laws so alien that we couldn't even imagine their behavior. The anthropic principle offers an elegant explanation. We find ourselves in a universe suited for life simply because we couldn't exist in any of the countless others that aren't. Out of infinite possibilities, only a handful of bubbles have the right ingredients for complexity, and we happen to inhabit one of them. If the multiverse truly stretches infinitely, there must also exist countless versions of you, identical in every detail except for the smallest variations. In some universes, you made different choices. In others, history unfolded along a completely different path. And sometimes, these vast bubbles even collide, producing cataclysmic effects that ripple across both realities. Mathematically, this concept can be expressed with a simple-looking equation: P1 E T This formula defines the probability that a bubble universe will form in any region of inflating space over a given period of time. As time stretches toward infinity, that probability approaches 100%. With infinite time and infinite space, the creation of new universes isn't just possible, it's inevitable. Eternal inflation operates like a cosmic casino where the house always loses. Picture flipping a coin endlessly. Each toss has a 50% chance of landing heads. Flip forever, and you'll not only get heads once, you'll get it an infinite number of times. The creation of bubble universes works the same way. Quantum fluctuations flip the coin of existence endlessly, ensuring that infinite universes will eventually arise. The key lies in understanding exponential growth. During inflation, the volume of space doubles over and over again in unimaginably tiny fractions of a second. This doubling never stops in regions where inflation continues. Even if the odds of forming a new bubble are minuscule, the rapidly expanding space ensures that bubble formation accelerates forever. It's like watching bacteria multiply in a petri dish. Each bacterium has a small chance of dividing in any given moment. At first, growth is slow, but as the population increases, so do the opportunities for division, until the colony explodes exponentially. Eternal inflation works the same way. Each region of inflating space has a tiny chance of producing a new universe. But because inflation keeps creating more space, the number of potential regions grows endlessly. The rate of universe creation keeps increasing, even though the local probability remains small. This leads to a mind-bending realization revealed by Andre Linde's chaotic inflation model. Every bubble universe forms with completely random physical properties. The strengths of gravity, the masses of particles, even the speed of light itself, all are determined by chance during each universe's birth. This randomness guarantees that an endless variety of physical realities exists across the multiverse. Some universes emerge where gravity is so faint that matter never binds into galaxies, while others form with electromagnetic forces so intense that atoms cannot take shape. Only a minuscule fraction develop with perfectly balanced constants, just right for complexity, life, and consciousness to arise. The anthropic principle offers an explanation for why we observe such finely tuned physics among infinite random outcomes. Conscious beings can only appear in those rare universes where the conditions permit their existence. We perceive a life-supporting cosmos simply because we couldn't exist in any of the others. Mathematical models also predict how frequently bubble collisions occur. When two bubble universes form close together, their expanding walls eventually meet and interact. These collisions leave behind permanent scars, subtle traces we might one day detect in the cosmic background radiation. Picture two floating soap bubbles, each containing its own miniature world. When they touch, their surfaces merge, forming a lasting bridge. Ripples from that impact spread through both bubbles, preserving evidence of the collision forever. The same principle applies to universe collisions, except here, entire realities are involved. During eternal inflation, bubble universes appear randomly throughout the expanding multiverse. Most remain eternally isolated, separated by vast regions of inflating space too immense for any contact. But if two bubbles emerge close enough in both space and time, their rapidly growing boundaries will eventually collide. Such an encounter generates gravitational waves that ripple through both universes. These waves carry distinct signatures determined by the collision angle, the relative speeds of the bubbles, and the contrast in their physical properties. Most significantly, these waves leave enduring marks in each universe's cosmic microwave background, CMB. Scientists have proposed how to detect such evidence within our own cosmos. If our bubble universe ever struck a neighboring one, gravitational waves from that ancient impact would have raced across space at light speed. They would have reached the surface of last, scattering, the moment when our universe first became transparent and emitted the CMB. This collision would have produced temperature fluctuations within the CMB following a very precise pattern. Unlike random variations, collision signals appear as circular rings centered on the impact's direction. The size and intensity of these rings depend on specific collision parameters. Physicist Matthew Johnson and his team at the Perimeter Institute created advanced simulations, predicting exactly how these signatures should appear in CMB maps. Their models provided detailed visual templates showing how different types of collisions would look. In 2010, researchers reported discovering 4 potential collision patterns in data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP. Each appeared as concentric rings of varying temperature, matching theoretical expectations. The findings hinted that our universe may have collided with 4 other bubble universes. However, later studies raised doubts. The European Space Agency's Planck satellite, which produced far more detailed CMB observations, indicated that those patterns were likely statistical coincidences, random fluctuations that can occasionally mimic circular ring structures. The search continues with even more refined analytical methods. Modern techniques can now distinguish genuine collision scars from random noise by analyzing multiple statistical properties at once. Discovering definitive proof of a bubble collision would completely reshape our understanding of cosmic reality. It would confirm that our universe is just one region within a vast multiverse of countless others. Such evidence would also give us the first observational insight into multiverse physics, revealing how universes form, evolve, and interact. Yet, even without direct proof, the ongoing search has uncovered fascinating theoretical implications. Bubbles where the laws of nature themselves operate differently. In some of these universes, electrons weigh as much as protons, and gravity repels instead of attracts. Every bubble forms with its own distinct set of randomly assigned constants: the strength of gravity, particle masses, light speed, and the intensity of electromagnetic forces, all selected from an infinite range of possibilities during bubble nucleation. Most combinations yield sterile realities where nothing complex can occur. Imagine a universe where gravity is 10 times stronger than ours. Stars would form quickly from gas clouds, but burn through their fuel in mere millions of years. Their violent explosions would unleash enough radiation to sterilize entire galaxies. Under such crushing gravitational conditions, no stable planets could exist. Conversely, picture a universe where gravity is 10,000 times weaker. In such a universe, matter would never gather into stars. Hydrogen and helium would drift endlessly through the void as a cold, thin mist. No fusion, no heavy elements, no planets, and no chance for life to exist. The electromagnetic force offers equally dramatic contrasts. If electromagnetism were slightly stronger, atomic nuclei would tear themselves apart, as the positive charges could no longer stay bound. If it were weaker, electrons would collapse into nuclei, erasing chemistry itself. Some bubble universes form under entirely different particle physics. In these alien realities, the fundamental components of matter follow completely different rules. Particles that attract each other in our universe might repel in theirs. Forces that weaken over distance here might instead grow stronger the farther they stretch. The most exotic scenarios involve universes that possess different numbers of spatial dimensions. Our reality contains 3 dimensions of space and 1 of time. But other bubbles could emerge with 4, 5, 10, or even hundreds of spatial dimensions. Movement in such higher spaces would be beyond human comprehension. Objects could approach from directions that don't even exist in our world. A 4-dimensional sphere, for instance, would seem to appear and vanish mysteriously as it passed through our 3D slice of existence. String theory suggests that universes with different numbers of compact dimensions may be quite common. These extra dimensions curl so tightly that we can't detect them, yet they subtly influence the nature of fundamental particles and forces. Some theorists even propose that advanced civilizations in other bubble universes might learn to control their local laws of physics. By mastering the deep relationship between space-time geometry and fundamental constants, they could potentially alter the very fabric of reality within specific regions. Such mastery would enable technologies that seem miraculous to us. Zones where gravity flows upward, where time runs at alternate speeds, or where matter transforms according to new rules entirely. The anthropic principle again comes into play here. Most universes in the multiverse remain barren, while only a tiny fraction develop conditions where complexity and consciousness can emerge. Intelligent life, therefore, is an exceedingly rare and precious phenomenon scattered across infinity. Yet our own universe might not be limited to strange physics beyond distant horizons. Some theories suggest that reality-bending phenomena could exist right here within our observable cosmos. Among the most fascinating possibilities are white holes, the theoretical opposites of black holes. While black holes consume everything that crosses their boundaries, white holes would do the reverse, erupting matter and energy outward so violently that nothing could approach them. Imagine cosmic geysers, hurling entire galaxies' worth of material into space. The same Einstein field equations that predict black holes also predict their mirror counterparts. General relativity describes how massive objects warp space-time, and when the equations are solved, two mathematical outcomes appear. One corresponds to matter collapsing inward, a black hole, while the other represents matter exploding outward, a white hole. Think of a film showing material falling into a black hole. Now reverse it. In that reverse movie, the matter bursts out from a single point, racing away at ever-increasing speeds. That's essentially how a white hole would behave. White holes could explain some of the most energetic cosmic events ever observed. Gamma ray bursts, for instance, release more energy in seconds than the sun will emit in its entire lifetime. Quasars blaze with the power of 1 trillion stars from regions smaller than our solar system. Active galactic nuclei hurl particles close to light speed across millions of light years. Standard theory attributes these phenomena to supermassive black holes consuming matter, heating it to extreme temperatures before it disappears beyond the event horizon. But some researchers speculate that white holes might offer alternate explanations for such cosmic violence. In our universe, though, a white hole would be highly unstable. Any matter approaching it would immediately disrupt its expulsion of material, causing it to collapse into a black hole. This instability might explain why astronomers have never observed a definitive white hole signature. However, in other universes, with different symmetries and laws, white holes might be stable and even common. There, they could act as cosmic engines, continuously creating the matter and energy needed to form galaxies. Some cosmologists even propose that the Big Bang itself was a colossal white hole event. Our entire observable universe may have erupted from a single point within a higher dimensional space, spewing out all the matter and energy that exists today. This white hole Big Bang model provides an alternative to standard inflation theory. The most daring theories go further, suggesting that black holes in our universe might be connected to white holes in others. Matter falling into a black hole's event horizon here could re-emerge from a white hole in a parallel universe, forming cosmic tunnels that link distant regions of the multiverse together. While white holes remain theoretical, other exotic structures almost certainly existed in the early cosmos and may still thread through space today. Imagine cracks in reality so thin they're invisible, yet so dense that just 1 kilometer of them outweighs Mount Everest. These are known as cosmic strings, one-dimensional defects in the very fabric of space-time. They are thought to have formed during the first fractions of a second after the Big Bang, as the universe cooled and fundamental symmetries shattered during rapid phase transitions. Think of how water transforms into ice. As the liquid cools and begins to crystallize, tiny fractures often appear where crystal regions meet. These cracks are small imperfections, places where the structure doesn't perfectly align. In the same way, the newborn universe went through phase transitions as its fundamental forces separated from one unified field. Along those boundaries, where different regions of space took on different properties, cosmic strings were born. The physics behind cosmic strings is beyond ordinary comprehension. Each one would be thinner than a proton, yet unimaginably dense. A single mile of it could outweigh the entire Earth. The gravitational pull around such an object would be powerful, enough to bend light and distort time itself. If they truly exist, cosmic strings would be nearly indestructible. Unlike normal matter, which can be shattered by force, these are topological defects, permanent distortions in space-time. To destroy one, you'd have to rewrite the fabric of reality itself. They remain as eternal scars, evidence of the universe's violent beginnings. Cosmic strings would also stretch to incomprehensible lengths. The shortest of them could reach across the entire observable universe, while others might extend far beyond our cosmic horizon into realms we'll never see. Some could form closed loops smaller than galaxies. Others might even bridge our bubble universe to neighboring realities. As they vibrate, twist, and collide, their movement would generate gravitational waves, ripples in space-time that detectors like LIGO could potentially observe. These signals would differ from the ones made by black hole or neutron star mergers. Some scientists suspect we've already caught hints of them. The Nanograv collaboration studies tiny irregularities in pulsar timing, ultra-precise cosmic clocks that emit steady radio pulses. Recent observations show patterns that may result from gravitational waves produced by networks of cosmic strings. Their immense gravitational influence could also have shaped the universe itself, drawing in matter and dark matter, forming linear structures that later became galaxies. If some strings connect our universe to others, they might even allow faint information to pass between realities. In theory, electromagnetic signals could travel along these strings, carrying messages between bubble universes that otherwise could never communicate. The search for cosmic strings continues. Astronomers use gravitational wave detectors, cosmic microwave background studies, and vast surveys of galactic structures to hunt for their traces. Discovering them would prove that reality hides structures far beyond imagination, threads of creation stretching through higher dimensions we're only beginning to grasp. Now, imagine two black holes spinning, together in perfect sync, ripping open a tunnel through the very fabric of existence. This might sound like science fiction, but Einstein's equations show that under very specific conditions, the extreme curvature of space-time could create shortcuts linking distant regions of the cosmos. Scientists call these wormholes. Creating one would demand unimaginable precision. You'd need two electrically charged black holes positioned at exactly the right distance. Their charges must be perfectly balanced. Too close and they'd merge, too far and they'd repel. To hold such a tunnel open, you'd need the help of cosmic strings. These one-dimensional space-time defects could act as cosmic scaffolding, keeping the passage stable. Remember, each string is thinner than a proton, yet denser than a neutron star. Their immense tension could theoretically prevent the wormhole from collapsing under its own gravity. Such a structure would form a stable tunnel between 2 points in space-time. You could step through one entrance and emerge instantly from the other, no matter how far apart they are. Travel time, essentially zero. Here's where bubble universes return to the story. If cosmic strings formed during the inflationary era, they might stretch between bubbles of reality in the vast inflating multiverse. A wormhole anchored by these interbubble strings could directly link separate universes. Imagine walking through such a tunnel and arriving in a world governed by entirely different physics, where gravity pulls in reverse, electromagnetism behaves backwards, or time itself flows at a different pace. It would be like stepping through one dream into another. Sadly, even theoretical wormholes are fragile. The cosmic strings that stabilize them would lose energy through gravitational wave radiation, shrinking until the tunnel collapses, often within microseconds. Yet some advanced theories suggest that quantum effects or exotic matter with negative energy could keep them open longer. In rare regions shaped by early cosmic inflation, stable wormholes might even form naturally. Perhaps in other bubble universes, advanced civilizations have already mastered this technology, creating and maintaining artificial wormholes to traverse their cosmos, explore distant realms, or even visit neighboring realities. If stable wormholes truly exist, they could solve one of the greatest challenges of cosmology, the isolation caused by faster-than-light expansion. Bubble universes that would normally remain forever out of contact might stay connected through vast wormhole networks. The consequences of this are extraordinary. Imagine a cosmic internet spanning multiple realities, where information, matter, and energy could flow between bubble universes that each follow their own unique physical laws. Scientists are still searching for traces of such wormholes in gravitational wave data and the cosmic microwave background. Finding even indirect evidence of these tunnels would prove that the barriers separating universes are not absolute. Yet some physicists believe that parallel realities could exist far closer than we think, perhaps running backward through time itself. In this view, for every second that passes forward in our universe, a matching second ticks backward in its mirror twin. This mirror cosmos was born at the exact same instant as ours during the Big Bang. Both share the same origin point, but evolve in opposite directions along the timeline. While we experience time flowing from past to future, the mirror universe experiences it in reverse, from future to past. This strange idea arises from the deep symmetries of physics. Most physical laws work perfectly, whether time runs forward or backward. Drop a ball and it falls. Reverse the sequence and it rises. Both obey the same laws of motion and gravity. The equations themselves have no preference for one direction of time over the other. But the second law of thermodynamics breaks that symmetry. In our universe, entropy, the measure of disorder, always increases. Hot coffee cools down. Shattered glass never reassembles. Life moves inevitably toward decay. Physicists Sean Carroll and others propose that the Big Bang may have produced two universes with opposite arrows of entropy. In ours, entropy increases as time flows forward. In the mirror universe, entropy increases as its version of time flows backward relative to us. Picture watching someone's life in reverse. They grow younger, lose knowledge, and return to infancy. That's how the mirror cosmos would look from our viewpoint. But beings within that universe would experience their time as normal, seeing their own history move forward, while ours seems reversed. Together, these twin universes create a perfect symmetry in cosmic evolution. Both began in a low entropy state at the Big Bang and have been climbing toward higher disorder ever since. The total entropy of the two combined remains balanced across all of cosmic history. The mirror universe would also be composed not of matter, but antimatter. Antiparticles carry opposite electrical charges and magnetic properties compared to normal particles. When matter and antimatter meet, they annihilate, releasing pure energy. Stars there would be made of anti-hydrogen and anti-helium, burning brightly through the same nuclear fusion we see in our stars. Anti-planets would orbit anti-stars in systems that, from a distance, would look identical to our own. If intelligent life formed in that mirror reality, those beings, made of antimatter, would view their world as perfectly natural, while finding our matter-based universe strange and exotic. This mirror universe hypothesis solves several long-standing cosmic puzzles. Why we observe so little antimatter, how time's arrow arises naturally, and even what dark matter might be. Some researchers propose that dark matter could actually be ordinary matter from the mirror universe, gravitationally linked to ours but invisible because it doesn't interact electromagnetically. The mirror realm would be just one example of countless parallel realities possibly existing in higher dimensional space, realms beyond what our senses can perceive. Space itself might curve in unexpected ways. Most people imagine it as flat, a boundless sheet extending evenly in every direction. Einstein's general relativity showed that massive objects curve space, producing what we experience as gravity. The overall shape of space, however, depends on the total mass energy of the cosmos. Our universe appears almost perfectly flat on the largest scales. Parallel lines remain parallel, and the angles of a triangle add up to 180 degrees. But other bubble universes could take on entirely different geometries. Imagine one with negative curvature, where space bends outward like a saddle. In such a reality, parallel lines would diverge over distance, and triangles would have angles adding up to less than 180 degrees. In this hyperbolic space, the shortest path between 2 points wouldn't be straight, it would curve. Navigation would be completely counterintuitive. Objects that seem to move in straight lines would actually follow arcs. Light rays would drift apart instead of staying parallel. Familiar geometry would give way to an alien mathematical landscape. The effects on cosmic structure would be immense. In flat space, gravity pulls matter together, forming stars and galaxies. But in a negatively curved universe, distances continually stretch apart, working against that clustering. Galaxies would struggle to form. Star systems would be unstable, their orbits tracing hyperbolic paths instead of ellipses. The cosmic web that connects galaxies in our universe might never emerge. Civilizations in such a reality would need completely different technologies. Their math would rely on hyperbolic geometry, not Euclidean principles. Their physics would incorporate curvature into every calculation. Some models even suggest that small regions of negative curvature might exist within our own universe, leftovers from cosmic inflation, or created by exotic matter with unusual gravitational behavior. Negative curvature could also exist in hidden spatial dimensions. String theory proposes that our reality may include 6 extra dimensions, compacted so tightly that they appear as tiny points from our 3-dimensional view. If any of those dimensions curve negatively, they could subtly affect the forces and particles we observe, shaping physics in ways that seem mysterious. Geometry is only one variable among countless others in the vast inflationary process, constantly generating new universes. Even as you read this sentence, trillions of new realities are coming into existence. The same cosmic inflation that gave birth to our bubble universe never truly stopped. It continues endlessly, stretching space-time and spawning infinite new worlds at an ever-accelerating rate. The eternal inflation engine runs on simple principles, yet it generates infinite complexity. Here's how this cosmic machine operates. Everywhere across the multiverse exists a mysterious energy field known as the inflaton field. It drives space to expand faster than light, stretching the fabric of reality itself. But this field isn't uniform. Tiny quantum fluctuations constantly nudge it above or below its average value in scattered regions throughout the expanding expanse. When these fluctuations push the field below a certain critical level, inflation halts in that region. The stored energy of the field then transforms into matter and radiation, igniting a hot Big Bang that cools over billions of years to form stars, galaxies, and perhaps life itself. Meanwhile, inflation continues everywhere else. The volume of space still inflating grows exponentially, opening up new areas where fresh bubbles of reality can form. This self-replicating process feeds endlessly on itself, an infinite chain reaction of creation. The numbers are almost impossible to comprehend. Every second, the total volume of inflating space multiplies by staggering factors, tens raised to unimaginable powers. Within this growing expanse, quantum ripples continually trigger the birth of new bubble universes, each expanding into existence at rates beyond human imagination. Picture bacteria multiplying inside an infinite petri dish that doubles in size every second. No matter how fast they reproduce, the available space always grows faster. Eternal inflation works in the same way, a cosmic mechanism that never stops producing new universes. Each bubble universe exists in total cosmic isolation. Once a bubble forms, the surrounding inflating space expands away from it faster than any signal can travel. These bubbles can neither communicate with each other nor sense the greater multiverse. Each one evolves independently, governed by its own randomly assigned laws of physics. Yet the eternal inflation process ensures that every possible combination of physical laws eventually appears somewhere. Some universes may have 10 spatial dimensions. Others may feature timelines that branch in multiple directions. There might even be realms where consciousness itself shapes matter. Quantum mechanics also predicts that exact copies of universes, including ours, must exist. The number of ways matter can be arranged in any finite region is limited. With infinite bubbles, identical universes become inevitable. Somewhere beyond our cosmic horizon, another Earth orbits another sun in another Milky Way. That twin Earth has the same continents, the same people, and the same history unfolding in perfect sync. The eternal inflation machine doesn't create one version of reality. It creates every version endlessly. Every possible outcome, every alternate decision, every branch of history plays out somewhere across the infinite multiverse. Physicist Andre Linde, one of the founders of inflation theory, calls this the ultimate Copernican revolution. Humanity once believed Earth was the center of the cosmos. Then we learned our planet wasn't the center of the solar system, nor our galaxy, the center of the universe. Now even our universe itself isn't central. It's merely one bubble among infinite others. Some of these universes may be so exotic, they would defy human comprehension. Imagine a cosmos with 10 spatial dimensions rather than 3. Our brains evolved to understand only the familiar dimensions of length, width, and height, plus time. But string theory suggests reality may include at least 10 total dimensions, with 6 hidden ones curled up so tightly that we can't perceive them. Think of a garden hose viewed from far away. It looks like a one-dimensional line, but up close, you see its circular surface, extra dimensions invisible from a distance. The hidden dimensions of string theory work the same way. At every point in our universe, 6 additional directions exist. All, the energy density of quantum vacuum fluctuations is believed to be immense. Theoretical estimates suggest that if all the virtual particle energy within a space the size of a coffee cup were added together, its total energy would surpass the combined mass energy of every visible star and galaxy in the cosmos. Here lies a deep cosmic enigma. This vast quantum vacuum energy should, in theory, generate a gravitational pull strong enough to warp space-time into a compact sphere. If that were true, our universe should have collapsed long before the first atoms ever came into existence. Yet instead of a crushed cosmos, we see a universe that's nearly flat, and has been steadily expanding for almost 14 billion years. Something must be offsetting the vacuum energy, preventing the universe from imploding. Scientists refer to this puzzle as the cosmological constant problem, and so far, its answer remains one of physics' greatest unsolved mysteries. Different bubble universes across the multiverse could hold unique relationships between quantum vacuum energy and the curvature of space-time. In certain realities, this vacuum energy may not be balanced at all, creating universes that collapse instantly into ultra-dense singularities. Others might possess negative vacuum energy, causing their space-time to stretch and expand even more violently than our own inflationary universe. But perhaps the most fascinating possibility lies in bubble universes where vacuum energy fluctuates randomly throughout space and time. Picture a cosmos where empty space sometimes outweighs matter, then suddenly becomes lighter. Regions with positive vacuum energy would curve space inward like invisible black holes, while those with negative energy would warp it outward, forming mysterious anti-gravity zones. In such a world, matter and light would follow strange, unpredictable paths as they move through regions of ever-changing gravitational strength. Stars could unexpectedly speed up or slow down as they pass through these fluctuating fields. Entire planets might have their orbits reversed or twisted into impossible patterns. Civilizations born in such chaotic environments would need incredibly advanced technology just to survive. Their spacecraft would rely on navigation systems designed to handle random gravitational distortions, and their cities would need to withstand constant shifts in the curvature of space-time itself. Some theorists even speculate that consciousness could interact with these quantum fluctuations through what's known as the observer effect. In universes where this effect is amplified, intelligent beings might literally manipulate their local space-time by directing focused awareness towards specific regions. In such realities, thought could directly shape matter, meditation might alter gravity, and collective consciousness could transform the very structure of space itself. These kinds of observer-dependent physics might occur inside bubble universes that form within black holes from other realities. Every black hole in our cosmos could, in fact, harbor a self-contained universe of its own. When a massive star collapses under its own gravity, it bends space-time so severely that not even light can escape, forming a black hole, the ultimate cosmic trap. But according to mathematical analysis, what happens inside these event horizons could be far more extraordinary. The collapsing matter may not simply compress into an infinitely dense point. Instead, it could ignite a new Big Bang, birthing an expanding universe within the black hole itself. From our viewpoint, the black hole appears frozen in time, with no way for information to escape. Yet from the perspective of the matter inside, time flows normally. As the material falls inward, it experiences mind-bending tidal forces that stretch and squeeze it into strange, exotic forms. Under these conditions, space-time itself might undergo a kind of phase transition, triggering inflation, much like our own cosmic beginning. It's like a seed germinating inside a sealed shell. From the outside, nothing appears to happen, but within, a complex new world begins to grow. Black hole universes would operate much the same way, entire realities evolving inside event horizons that appear still and silent to outside observers. Mathematical models even suggest these inner universes could be vastly larger than the black holes containing them. This only seems impossible until one remembers that space-time itself is curved and connected in non-intuitive ways. Physicist Lee Smolin proposed that this cosmic reproduction might explain why our universe's physical constants seem so finely tuned for life. If universes capable of producing more black holes also generate more offspring universes, then natural selection could apply on a cosmic scale, favoring the physics that make black hole formation more likely. Our universe, after all, produces billions of black holes through stellar evolution. Each one could potentially give birth to a new pocket universe with slightly different laws of physics. Over countless generations, this cosmic evolution might fill the multiverse with realities optimized for black hole creation. Some of these offspring universes might possess stronger gravitational forces, allowing massive stars to form more easily. Others could have altered nuclear reactions, enabling stars to grow larger before collapsing. Each generation would thus become better at reproducing, not biologically, but cosmically. This idea of evolutionary cosmology implies that we may be living in a universe descended from a long ancestral chain of black hole universes. Our own laws of physics could exist precisely because they've proven successful at birthing new black holes in previous generations. Some bubble universes might take this even further, becoming vast stellar nurseries filled with billions of times more black holes than ours, each one a cradle for new cosmoses waiting to emerge. And beyond these, colossal structures lying past our cosmic horizon might pull entire regions of matter through forces unlike any we've ever imagined, including one so massive, equal to 10,000 Milky Way galaxies, drawing our entire universe toward the distant constellation Hydra. The Milky Way galaxy races through space at more than 1,000,000 miles per hour, a motion that can't be explained by cosmic expansion alone. Our galaxy, along with thousands of its neighbors in the local group and Virgo cluster, is being drawn toward an unseen gravitational giant located about 250 million light-years away. Astronomers call this mysterious force the Great Attractor. What makes the Great Attractor so puzzling is that when scientists aim their telescopes toward its direction, near the Hydra constellation, the region looks surprisingly ordinary. Yes, there are galaxy clusters there, but nothing massive enough to pull on our entire galactic neighborhood with such intensity, even after accounting for the zone of avoidance, a section of the sky where the Milky Way's own dust clouds obscure distant space. Astronomers still can't find enough visible matter to explain its gravitational power further. Research revealed something even stranger. The Great Attractor itself is being pulled toward an even more colossal structure known as the Shapley supercluster. This enormous complex of galaxy clusters contains the gravitational equivalent of 10 quadrillion suns, spread across hundreds of millions of light-years. But even that isn't the end of the cosmic hierarchy. Recent maps of galactic motion show that our entire local region, including the Great Attractor and Shapley supercluster, is moving as part of an even greater flow towards something unimaginably vast. A structure so immense that most of it lies beyond what our telescopes can observe. Scientists call this phenomenon the dark flow. To visualize it, imagine drifting down a river toward a massive waterfall. You can feel the current tugging you forward, but you can't actually see the drop ahead because it lies beyond your view. The Great Attractor and dark flow behave the same way. We can detect their gravitational pull on nearby galaxies, yet the true source of that pull may exist far beyond the edge of our observable universe. Some cosmologists propose that the Great Attractor might be a gigantic clump of dark matter, a leftover imprint from the earliest moments of cosmic inflation. During that explosive epoch, quantum fluctuations could have created density ripples on scales much larger than our visible universe. What we see might just be a small fragment of one of these enormous, unseen megastructures. Other theories reach even deeper into the fabric of reality, suggesting that the Great Attractor might actually be the result of extra-dimensional physics. Massive objects existing in higher dimensions could exert gravitational influence on our three-dimensional space while remaining completely invisible to our instruments. Shadows of a larger, unseen reality pressing against our universe. If such hidden, extra-dimensional entities truly exist, they could point toward bubble universes, where the very foundations of physics operate under entirely different rules. In some of these alternate universes, for example, like charges attract while opposite charges repel, a complete reversal of electromagnetism as we know it. In such a universe, atoms as we understand them could never exist. Positively charged protons would violently repel one another, preventing atomic nuclei from forming. No stable electrons could orbit around them, meaning chemistry would never happen, and life, at least in any recognizable form, would be impossible. Yet reversed electromagnetism could also allow completely new forms of matter to emerge. Imagine particles with the same electric charge clustering together into stable, crystal-like structures. Gravity would pull them inward, while their mutual repulsion kept them from collapsing entirely. The delicate balance between attraction and repulsion could give rise to exotic matter with properties beyond anything known in our universe. These charged structures might form hollow frameworks with intricate internal geometries sculpted by the push and pull of competing forces. On a cosmic scale, galaxies in such a reality would evolve in astonishingly different ways. Plasma would behave in reverse. Magnetic fields could focus matter instead of scattering it. Stars might form not through gravitational collapse, but through electromagnetic attraction. In other bubble universes, electromagnetism might be far stronger or weaker than in ours. If stronger, atoms would grow larger and chemical bonds would hold with immense energy, creating complex, hyper-reactive molecular systems, perhaps enabling new forms of chemistry and life. If weaker, atoms would shrink until quantum effects ruled everything. Matter in those universes might behave more like a continuous quantum fluid than a collection of particles, allowing intelligence based on quantum coherence rather than classical thinking. The strangest possibility of all involves universes where electromagnetism itself splits into multiple separate forces, each with unique strengths and behaviors. In such alien realities, even the concept of light, matter, and charge could operate under principles utterly foreign to human understanding. Instead of one unified electromagnetic field, these alternate realities could host separate electric and magnetic forces, each operating on its own. Civilizations born within such universes would build their entire technology around manipulating these forces independently. They might craft materials that react only to electricity while ignoring magnetism, or the other way around. Their electronic systems would follow engineering, principles completely alien to anything humans could comprehend. Some of these bubble universes might even contain entirely new fundamental forces that have no counterpart in our physics. These exotic interactions could hold matter together in ways that make stable structures impossible in our own reality. Beings in such universes might master these mysterious forces, reshaping matter at will, traveling instantly across unimaginable distances, or transforming energy directly into patterns of pure information. The countless variations of electromagnetic behavior represent just one tiny glimpse of the infinite diversity that may exist across the eternal multiverse. And fascinatingly, this electromagnetic diversity might be interconnected through vast dark matter networks spanning multiple realities at once. Dark matter could serve as the cosmic web of the multiverse, an invisible internet linking infinite worlds together. In our own observable universe, galaxies form clusters along enormous filaments of unseen matter stretching billions of light years across space. These dark matter filaments act as highways of mass, guiding the flow of galaxies and energy across the cosmos. Astronomers map this structure by observing how its gravity bends light from distant galaxies, a technique known as gravitational lensing. Without this invisible framework, galaxies would drift in random isolation instead of organizing into the majestic cosmic patterns we see today. But here's where the theory becomes truly revolutionary. The cosmic web might not stop at the edge of our universe. If dark matter formed before the inflationary expansion separated bubble universes, the same filaments could stretch through multiple realities simultaneously, physically linking them together. Picture the underground mycelium networks that connect trees in a forest. Above ground, each tree seems independent, yet beneath the soil, their roots are bound through hidden channels that share nutrients and information. Similarly, bubble universes might be rooted together through dark matter filaments that let gravity, or even data, ripple from one universe into another. This could help explain enigmatic phenomena like dark flow, where clusters of galaxies in our universe appear to drift towards something massive beyond the cosmic horizon. If these hidden filaments cross into other universes, they might serve as conduits for gravitational effects or even information exchange between advanced civilizations across realities. Some theoretical models propose that dark matter might exist in higher spatial dimensions we cannot perceive. These extra-dimensional filaments could intersect multiple 3D universes at once, forging gravitational bridges between otherwise isolated realms. Advanced civilizations might one day learn to engineer dark matter itself, shaping its density and flow to manipulate the gravitational field around their worlds, or even to open pathways to neighboring universes. The cosmic web could function as a transportation network, where stable, wormhole-like channels enable travel across the inflating multiverse. If scientists could map the full structure of this dark web, they might uncover which universes remain connected to ours, and which ones have drifted into total isolation. Understanding this network could reveal the topology of the multiverse and show how bubble universes evolve, merge or separate over cosmic time. Ultimately, this dark matter web may hold the key to interuniversal communication, our best hope of one day detecting or even reaching other realities beyond our own. Yet, some universes may host forms of intelligence so advanced that they no longer rely on physics alone. Instead, They might create new realities through the sheer power of conscious observation. In these worlds, consciousness itself could be the most fundamental force in existence. Quantum mechanics already hints at this strange connection. The act of observation doesn't just reveal reality, it changes it. Before being measured, particles exist in multiple states at once, a mysterious condition known as superposition. The famous double-slit experiment shows that electrons can travel through two different paths simultaneously, until someone observes which path they take, collapsing their potential into a single reality. This mysterious observer effect hints that consciousness itself may directly shape physical reality. In our universe, this influence seems almost negligible. You can't shift mountains by thought alone or change the orbit of planets through meditation. On large scales, quantum effects fade, drowned out by the warmth and mass of the macroscopic world. But what if some bubble universes evolve differently, where quantum effects never fade, remaining powerful at every scale? Imagine a cosmos where the boundary between the quantum and classical worlds never forms at all. In such a realm, conscious observation could literally influence the behavior of stars, galaxies, and even space-time itself. In these realities, intelligent beings might think matter into existence, sculpting the fabric of the cosmos through sheer awareness. The mathematics of quantum mechanics does not forbid this. In fact, it allows for it. If decoherence never collapses superpositions naturally, then even planets and suns could exist in multiple states at once, until consciousness chooses which version becomes real. Civilizations within these observer-dependent universes would evolve in ways completely foreign to us. Rather than building machines to shape the physical world, they might train their minds to manipulate reality directly. Their technology would be powered not by circuits or engines, but by awareness itself. Such beings could summon objects into being through imagination, travel across cosmic distances simply by observing themselves elsewhere, or even rewrite the laws of physics through collective intention. Their societies would be founded on a profound truth. Reality responds to consciousness. Some cosmologists have proposed a staggering idea that consciousness might be necessary for any universe to exist at all. This view, known as the participatory universe hypothesis, suggests that worlds without observers remain trapped in quantum uncertainty, never solidifying into a definite state. If true, that would mean bubble universes lacking awareness exist only as ghostly probabilities, unrealized dreams of physics. Only those that give rise to intelligent life would collapse into full existence, becoming concrete realities. This creates a cosmic selection effect, where awareness itself determines which possible universes are actually real. The multiverse, then, would be dominated by realities containing consciousness, because only such worlds can exist in the first place. And in time, the most advanced forms of consciousness might even learn to observe and awaken other universes, bringing them into existence through focused attention. These beings could act as cosmic creators, transforming potential into reality by choosing what to observe. In this sense, the observer effect may not just describe quantum mechanics. It might explain why our universe appears so perfectly tuned for life. If consciousness is required for reality to exist, then all observable universes must naturally contain the conditions that allow consciousness to arise. And yet, there's an even deeper possibility, one that shifts the mystery from the mind to the machine. What if our entire reality is a simulation? What if everything you see, feel, and think is code, running inside a vast computer built by beings from another universe? This idea, known as the simulation hypothesis, proposes that what we experience as physical reality is actually a high-resolution digital construct. A simulation so detailed that every atom, every star, even your thoughts, are part of a massive computational process. Far from being mere science fiction, the mathematics behind this theory is strikingly persuasive. A civilization advanced enough to wield immense computational power could simulate entire universes, each governed by its own physical laws and histories. If such technology is possible, then statistically, there would be far more simulated worlds than original ones, making it overwhelmingly likely that we ourselves are inside one. Now, imagine applying this concept to the multiverse. If our universe is a simulation, then the computer running it must exist in another universe, one level higher in the hierarchy of realities. But what if that universe is simulated too? This creates a dizzying structure of nested realities, stacked like Russian dolls, each one simulating the next. The beings who run our simulation might themselves be digital entities created by still higher level beings. The chain could continue endlessly. A staircase of simulations reaching deep into infinity. Each level of this hierarchy would face its own computational limits. The base level universe, the real reality, would have access to all physical resources. Every layer above it would have slightly less power, since some of its energy must be devoted to running the simulation below. Eventually, this cascade would reach a breaking point, a level so deep that no further simulation could exist, because the computational cost would exceed the available energy. Beyond that threshold, the digital chain of realities would collapse, leaving only the final, fundamental universe, the one from which all others are born. Civilizations may one day overcome the limits of their simulated worlds, not by escaping them, but by rewriting the code itself. Advanced beings could develop hyper-efficient algorithms, allowing them to simulate countless realities with minimal computational cost. Some might even learn to harness physical phenomena within their own universe, tapping into the fundamental processes of nature for limitless computing power. Through the mastery of quantum computation, such civilizations could access the computational energy of parallel universes via superposition. In theory, a single network of quantum computers, spanning an entire reality, could simulate infinite universes simultaneously, each with its own physical laws, timelines, and civilizations. This perspective also sheds light on the peculiar constraints of our own universe: the speed of light, quantized energy levels, and immutable physical constants. These might not be natural boundaries at all, but computational shortcuts coded into the simulation to conserve processing power. Just as video games use simplified physics to keep frame rates smooth, our cosmic program may employ approximations that balance realism with efficiency. If that's true, then what we call laws of physics are really the resolution settings of the cosmic engine. And like any simulated environment, glitches may exist, subtle anomalies revealing the computational skeleton of our universe. Physicists already search for these cracks in reality: pixelation in space-time, energy quantization beyond known limits, or inconsistencies in quantum complexity that hint at underlying code. The simulation hypothesis may not answer everything, but it offers a profound possibility that existence itself is information. That reality is computation, and that creation never truly stops. It only restarts, because even if our universe is simulated, every simulation must end. And when it does, what follows is not destruction, but rebirth. As our universe expands, dark energy continues to accelerate the cosmic flow, flinging galaxies farther apart. Over trillions of years, every galaxy will drift beyond every other's reach, each isolated in its own bubble of space and time. Stars will burn out, white dwarfs will fade into cold black remnants, neutron stars will decay, even black holes will evaporate through Hawking radiation, their mass dissolving into faint whispers of energy across unimaginable spans of time. What remains will be a silent ocean of darkness, a universe of fading particles separated by distances larger than imagination itself. This is the heat death of the cosmos, the moment when entropy reaches its maximum and no energy remains to fuel creation. But the story doesn't end there. Even in this emptiness, quantum fluctuations will stir. Tiny ripples in the vacuum will occasionally create pockets of false vacuum, new seeds of inflation. Each fluctuation could ignite a new universe, expanding outward to begin the cycle again. Just as a forest fire clears the way for new growth, the death of one universe paves the path for countless new realities. Physicist Roger Penrose envisioned this in his theory of conformal cyclic cosmology, a cosmic loop where the infinite future of one universe connects seamlessly to the birth of the next. Information from our dying cosmos might even survive the transition, encoded in faint patterns of the cosmic microwave background, like messages written across eternity. In this eternal cycle, death becomes creation, and every ending gives rise to infinite beginnings. Each universe, unique and unrepeatable, adds another verse to the endless poem of existence. Some will mirror ours, others will follow laws we could never comprehend, and perhaps some will be born from the will of consciousness itself. If awareness truly shapes reality, then intelligent civilizations facing the end of their worlds might embed their essence into the quantum foam, seeding new universes with fragments of their knowledge, their stories, their dreams. In doing so, consciousness achieves immortality, passing from one cosmos to the next, guiding the birth of infinite futures. Because in the grand design of the multiverse, nothing is ever lost. It only transforms. Every collapse is a new beginning. Every void becomes a cradle, and from every silence, the universe learns to speak again. Perhaps somewhere beyond our horizon, another civilization watches their universe die, not in despair, but in awe, knowing that every ending writes the first line of a new creation. And maybe that's how our own story began.